Recall that in analysis, we studied that given a function f from R to R, which is differentiable at all points and the derivative at every point is equal to 0, then the function has to be a constant function. And the proof of this result was a simple application of the mean value theorem. More precisely, we proved this theorem using a proof by contradiction. We assume the function is not constant, which means there exist 2 points a and b such that f of a is not equal to f of b, and then you apply mean value theorem to the interval a comma b. Then you will get a point c in between a and b where the derivative is not equal to 0. And that is a contradiction, therefore f has to be a constant. Now let us modify this question a little bit. Instead of a function that is differentiable everywhere, we consider a function that's differentiable at all points except 0. And whenever x is not equal to 0, we know that f dash of x is equal to 0. What can you conclude about f in this case? That's the next question. Notice that we cannot use the earlier proof. Because if the 2 points a and b are on 2 different sides of 0, then we cannot apply the mean value theorem on the closed interval a comma b. Why? Because there exists a point 0 in between where the function is not differentiable. Thus, we cannot conclude that f is a constant. However, notice one thing. If you take 2 points a and c that lies to the left of 0, or you consider 2 points b and d that lie to the right of 0, then we can apply mean value theorem to the intervals ac and bd. From this we can conclude that the function takes at most 2 different values. One value for all negative x's and one value for all positive x. And a third value may be at 0, because at 0 we cannot really conclude anything. So finally, we can conclude that it has the form f of x is equal to a if x is greater than 0 and b if x is less than 0, where a and b are 2 constants. Now let us ask a similar question for functions f from Rn to R. For simplicity, we are going to take n is equal to 2. So consider a function f from R2 to R that's differentiable and its gradient is equal to 0, 0 at all points. Then what can we conclude about this function? That's the question that we are now interested in. We guess that once again this function f has to be a constant, and we try to prove this using a proof by contradiction. So to use a proof by contradiction, we assume that there exist 2 points x1, y1 and x2, y2 such that f of x1, y1 is not equal to f of x2, y2. And using this, we would like to reach a contradiction. Given these 2 points x1, y1 and x2, y2, we can consider a line segment that joins these 2 points. More precisely, we are looking at the function L from 0, 1 to R2 defined as L of epsilon is equal to x1 plus epsilon times x2 minus x1, comma y1 plus epsilon times y2 minus y1. Notice that L of 0 is equal to x1, y1 and L of 1 is equal to x2, y2. Further notice that if you consider the function f composed with L from the interval 0, 1 to R, then we are restricting our attention to this particular line. And an arbitrary point f composed with L of t would be a point somewhere here. So the derivative of this function with respect to t will give you the directional derivative of the function f along this direction. In other words, we can see that f composed with L dash at t is the directional derivative of f at the point L of t along the direction x2 minus x1, comma y2 minus y1, which we know is equal to grad f at L of t dot product with x2 minus x1, comma y2 minus y1. Now we know that the gradient of f at every point is equal to 0, which would mean that f composed with L dash at t is also equal to 0 at every point. However, notice that f composed with L at 0 is equal to f of x1, comma y1, which is not equal to f of x2, comma y2, but f of x2, comma y2 is nothing but f composed with L of 1. So once again you have a contradiction, and thus this function has to be a constant. Now notice that there is one part of this where we did a little bit of hand waving, and that is in this equality. Of course, we intuitively understand why this is true. However, we have not really proved this fact. However, bear with me for some time and we will see a rigorous proof later. Once again, let us raise the difficulty and ask one more question. This time, we are not going to assume that the function is differentiable at all points. We are only going to assume that it's differentiable whenever x, y is not the origin. And at all points apart from origin, we want the gradient to be equal to 0, 0. If this is the case, what can we conclude about f? Recall that we were unable to conclude f is a constant when we did not have differentiability at the point 0 when we were studying functions f from R to R. However, this was because when you removed 0 from this line, we got two different pieces. These are two different pieces, and in each of these two pieces, we could conclude that the function was constant. However, when we consider R2 minus the point origin, then the resultant set is still one piece. At least it looks like one piece to us. Therefore, the earlier intuition that the function has to be constant on each piece should tell us that the function f should be a constant. However, if we mimic the earlier proof, we might run into some trouble. The idea of the earlier proof was as follows. We assume that f is not constant, which would mean that there exist 2 points, say x1, y1 and x2, y2, where the value of the function is not equal. And then we considered the line segment joining these 2 points. As you can see in this example, it is possible that this line segment passes through the origin. If it passes through the origin, then we do not know the value of the gradient at origin, and hence we are in trouble. Thus, we cannot blindly mimic the proof that we had done earlier. That said, we can bypass this problem using a small trick. We can consider the point x2, y1 and the two line segments that join these two. In other words, we are considering a different path from x1, y1 to x2, y2. And there are only two possibilities. Either f of x1, y1 is not equal to f of x2, y2, in which case there will be some point in between these 2 points where the gradient has to be non-zero. Otherwise, f of x2, y1 has to be different from f of x2, y2, which means that there is some point in this line segment where the gradient is non-zero. So either way, there will be some point where the gradient is going to be non-zero. Here, notice that when I say non-zero, I am meaning it as a vector, a non-zero vector. So whatever be the case, we have found a point where the gradient is non-zero. However, notice that the path that we take to connect x1, y1 and x2, y2 depended on the 2 points x1, y1 and x2, y2. We cannot give a general algorithm. For example, even if we took the black path as the algorithm, that will not always work. For example, if the x1, y1 was this point and x2, y2 was this point, then the black path will pass through the origin and therefore it is not a valid path. So there is no general algorithm that we can give for the path that we need to construct. It will depend on the points x1, y1 and x2, y2. We can complicate the question even further by saying that we do not know about the differentiability of the function inside the unit disk, but outside the unit disk, the function is differentiable. Moreover, the gradient is equal to 0, 0. In this condition, what can we say about f? This is the next question that we can ask. In this case, when we try to mimic the earlier proof by considering 2 points x1, y1 and x2, y2, it is possible that the straight line joining the 2 points and the path that first goes right and then goes up both pass through the problematic region. So, if we want to take a path that avoids the problematic region, we will have to look at more general paths. We might have to look at a path that looks something like this. More precisely, we are looking at some curve from 0, 1 to R2 such that gamma of 0 is equal to x1, y1 and gamma of 1 is equal to x2, y2. And we are looking at the function f composed with gamma. We would like to prove that f composed with gamma dash at t is equal to 0 for all t. This is what we would like to prove. Why? Because if we have this, we can apply mean value theorem on the closed interval 0, 1 for this function and get a contradiction, as we had done in all the previous cases. So it's enough if we prove this. And recall that in the earlier case where this curve was just a straight line joining the 2 points, we could observe that f composed with L dash at t is equal to the gradient of f at the point L of t dot product with x2 minus x1, y2 minus y1. But this x2 minus x1, y2 minus y1 was nothing but the derivative of L at t. So in other words, we would like to claim that this quantity is equal to gradient of f at the point gamma of t dot product with gamma dash of t. If we can prove this, then we know that gradient of f at gamma of t is equal to 0. Therefore, this dot product is also equal to 0. Once again, when I say the gradient is equal to 0, I am meaning that it is the 0 vector. Also notice that when we do this equality, we are using the fact that gamma lies outside the problematic region. So therefore, if we manage to prove this, then we have our theorem. So the question is, can we prove this theorem? Can we prove that f composed with gamma dash at t is equal to gradient of f at gamma of t dot product with gamma dash of t? And notice that this has a familiar form. Gradient of f in some sense is the derivative of f and gamma dash is the derivative of gamma, and we are taking the product of those two. Of course, here we are taking dot product, but it's very similar to the product. Therefore, this should remind you of the one variable theorem that if f and g are two functions from R to R, then f composed with g dash at x is equal to f dash at g of x into g dash of x. And this was called the chain rule when we studied analysis. So whatever result we want to prove is an analog of this chain rule. And therefore it will be called chain rule in this higher dimensional set. And this will be the content of the next video.